The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're talking about the brilliant and gross ways that science discovered in the trenches makes it to the bedside. We'll speak with Captain Mark Riddle of the United States Military Diarrheal Diseases Vaccine Research Program. What does he do? Just what it says on the tin. We're also speaking with George Peck, a medical entomologist, who will tell us what fly maggots have to do with keeping open wounds clean. Welcome to Science for the People. I'm Bethany Brookshire, a science writer with Science News and Society for Science in the Public. I'm here with Captain Mark Riddle, the director of the United States Military Diarrheal Diseases Vaccine Research Program. While reading Mary Roach's book Grunt, The Curious Science of Humans at War, I came across Mark's research on diarrhea. While many of us are aware of the perils of the stomach that can occur when we eat while traveling, Mark's research made me realize just how much of an issue this can be in the military, and taught me a lot about what we can do to prevent and treat our next gastrointestinal bug. Mark, thank you so much for joining us.
Bethany, thanks for your interest.
I wanted to start by defining our terms. What does it mean to have diarrhea? I mean, other than the visceral experience.
Yeah, that's a very deep question as well. It's interesting. The way you define diarrhea kind of depends on how you're approaching it and whether you're in a travel setting or whether you're in a clinical setting, whether you're dealing with children or adults. And in simple terms, it's a change in the consistency of your stool towards a more loose or liquid consistency, as well as a change in the frequency. The issue is that there's wide variation in people's stooling patterns and habits. And so, it's normal to have 3 stools a day, but it's also normal to have 1 stool every 3 days, or, so there's normal, patterns that range widely. So I think in terms of traveler's diarrhea or infectious diarrhea, even anything diarrhea that's caused by infection, we have a classical definition that we use, and that's 3 or more loose liquid stools in a 24-hour period. And it's thought that if you're in an environment where you're traveling, or you're a child in the developing world or even an adult in the developing world, and you have 3 or more loose stools in a 24-hour period, it's likely caused by an infection. And then you get to the definition of what's loose and liquid. And we actually have ways of determining that. I mean, what we use a lot in terms of the research realm is if it takes the form of a container, then it's loose or liquid. I have some colleagues that like to be funny, and they tell me the way they define whether it's loose or liquid is that if it can be sucked up through a straw, it's loose or liquid. but I've never tried that.
I really hope they don't know this from experience.
I hope not either.
So a loose stool is measured by a delightful metric known as a stool scale, which is about one of my favorite things in the medical literature. I was wondering if you could tell us about your stool scale and how it differs from the more widely known Bristol stool scale.
Sure. And yeah, for the listeners, it's not a scale that you put something on. It's a scale that, kind of measures the consistency. So the one that we use, and is widely used in research, studying infectious diarrhea is a 5 scale. And let me think as I talk through it. So a 5 is a very firm, think of a Tootsie Roll.
I really don't want to think of a Tootsie Roll right now.
So that it's hard, it's firm, it's not constipated, but it's well formed. And say then a 4 would be, really, formed soft serve ice cream. So something that keeps its shape. And I don't mean to gross out your listeners, but most people can relate to these food consistencies. So a 3 then, and a 4 and a 5 are normal. And so a 3 then is something that is more like a pudding or a runny milkshake. So it's very thick and viscous, but it takes the form of a container, as we were just talking about. A 2 starts to get where you see a lot more clear liquid and little bits and pieces in it. And so it's kind of a more watery. And then a 1 is like completely watery, just clear, clear or cloudy water. So that's how we define whether it's diarrhea. And it's important to know because some things like cholera or enterotoxigenic E. coli, it can cause a 1, mostly 1. So you're just, you're just leaking water, basically. So compared to the Bristol scale, the Bristol scale is by the British, and so everything's a little bit more precise. And it's a visual scale. And it covers the similar types of stool, but it's a 7-point scale, and it goes all the way from something that's very formed, but includes like hard pellet stool that is related to constipation, and then it goes all the way to the very, very watery stool. The Bristol stool scale was really designed to measure all sorts of bowel consistency, of chronic constipation, of malabsorption, and so it's got a few more gradations, and it's meant also for the patient to be able to have this scale, and then when they go to the bathroom, they look and they can record specifically what their stool looks like. In the research world, we're generally taking in stool, we're grading it ourselves. And so we do a lot of the grading, but in actuality, we some of our trials, we have, visuals as well. So we have, 5 jars, one with a Tootsie Roll, and with basically with things that look like the grade that they're in. So that's kind of the main difference.
You have ruined chocolate desserts for me for all time. I will never look at pudding the same way again.
Sorry. Maybe you should edit that out.
No, that's fine. And as we've kind of established, diarrhea is a, shall we say, running joke.
Yeah, yes, I've heard that before.
In most developed countries, but through history and actually even today, it's a very significant issue. It's an especially tough problem on the battlefield. What has been the history of diarrhea in war?
Well, yeah, it goes back many years. Even before kind of modern recorded history. There's accounts of diarrhea in battle, and large people dying of dysentery or of problems. I would say, in the modern historic times, starting from the Civil War on, it's also played a prominent role. In the Civil War, there was an old saying that, it takes good guts to be a soldier. And part of that was that, you had to have a real strong constitution. Otherwise you would get sick on the battlefield all the time. There were kind of unwritten rules that, if a man was so sick and was having to go to the bathroom, just in the middle of the field, that there was a soldier's creed that you wouldn't shoot at that person. I mean, it was just because it was such a common, and I think men in battle found, found sympathy in that. There are stories of campaigns in Napoleon where large groups of people were taken down by dysentery, and in the pre-antibiotic era, often more men would die of dysentery than malaria or any of these other infectious diseases. So significant. Since World War II, it did have some problems there. Rommel, the German, general in North Africa, and he claims that it wasn't the British that defeated him, or in total, but it was also dysentery among his men that caused them to lose the battle, and that was in Alamein. And then in modern times, I think, looking in Vietnam, again, more diarrhea than malaria in Vietnam, and still a significant problem. But we started to learn our lessons about hygiene and how to control food and water sources, and that kind of changed it, and it started becoming less frequent, so to say. I think now it's often considered more of a battlefield nuisance, but I don't think we really know. I have a good colleague of mine who's a British gastroenterologist, and he describes a story in Afghanistan where some military personnel were out on a patrol, and they were getting sick with diarrhea and dysentery and losing weight. And they come back and one of them steps on an improvised explosive device, and he's interviewing them all and learning kind of what it was like out there and how things have happened. And it raises the specter that, if you're so preoccupied with, if you're dehydrated because you've been stooling so much, you've got cramping, you're wondering where you're going to go to the bathroom next. How are you really paying attention to some of these danger cues that you see? Is it possible that actually diarrhea, even in today, could contribute to mortality? So while we have better treatments for it and we have better food and better water, those are still we're still challenged by the illness that is very common and still impacting our military forces in doing their job. So much so that, like you mentioned at the beginning, we have a major vaccine program where we're trying to develop vaccines to prevent these illnesses in the first place.
You say it's still pretty common. How high is the rate of diarrhea now among troops in, say, the Middle East?
Yeah, so in the Middle East, it depends on it depends on a lot of things. It depends on, are you going to a facility where we say it's hardened, where you're getting all your food at a dining facility, you have flush toilets, you're eating meals that are prepared based on current standards of preparation. And so, in that situation, the attack rates are about 10% per month or so. But if you're out on patrol and you're exposed, eating off the street and things like that, the rates can be up to 80% per month. A good rule of thumb that we use on average is that about 30% per month develop what would meet the definition of traveler's diarrhea. So about a third per month in these austere places. That's
very high. How does that compare to diarrhea in the local population?
Yeah, so the local population, it's a good question. We in kids in the developing world up till about the age of 5, they're getting about 5 to 8 episodes a year of diarrhea. So I guess if you calculated 30% per month, then that would be about 4 episodes per year of a soldier living, if you were living in one of these over for a year. So it's a little bit more kids in the developing world. But by the age of about 5, the rates of diarrhea go down because children, you develop immunity. It takes a while, but you eventually, your body has seen all the different variety of things that can cause diarrhea, and you acquire immunity, and you don't get as sick as much. You still get it. but not as frequent. And then when you get older in the developing world, when your immune system starts to wane, then you start getting more infections. And
what actually causes these cases of diarrhea?
Yeah, so there's a lot of things. It's and it depends on the population, and it depends on the country that you're in. There's regional differences. But I'll start with the travelers first, or any adults that travel overseas. It's about 85 to 90% bacteria. And we know that because we've done studies where you give people an antibiotic to take every day, or you give a person a placebo, a sugar pill to take every day. And those that are taking the antibiotics will be protected anywhere from 85 to 90% of the time. But we don't advocate taking antibiotics for travel. There's safety concerns, but that's informed the fact that it's predominantly bacteria. Now, if you or I or anybody gets sick in the United States or the developing world, it's predominantly virus, and that's what causes it. In the developing world, the kids in the developing world, it's early on, it's predominantly viruses, rotaviruses and norovirus, and bacteria. So it kind of depends. In terms of traveling, we also say that it's about maybe 10% also is virus. Norovirus is probably the most common one. And then very few, less than 5% or less than probably 2 or 3% are parasites like Giardia or amoeba or cryptosporidium, those kind of things. Generally, you get more parasites as you stay longer in places, or if you're even more exposed, eating off the street a lot or living amongst the locals. Think of aid workers that are working in refugee camps where you're really exposed to the fauna and flora of the environment. So, but bottom line is for travelers and military, it's a vast majority is bacteria. Now, it's a lot of bacteria. There's like 7 different flavors of E. coli. There's enterotoxigenic E. coli. There's intraaggregative E. coli. There's enterohemorrhagic E. coli. The list goes on. But there's also things like Shigella, Salmonella, Campylobacter. Those are all common as well. And so it's a real challenge because there are so many things that can cause traveler's diarrhea. And then even among the bacteria, there's such a variety of things that cause it. But there are things that cause it more commonly, like enterotoxigenic E. coli, intraaggregative E. coli, norovirus, Shigella, Campylobacter. And so those are the ones that we're focusing on developing vaccines for.
Mark, while bacteria and viruses and parasites, but mostly bacteria, do the sickening in terms of giving someone diarrhea, it's actually flies that do the spreading, right?
Well, flies certainly play a role. A number of studies have shown that flies that land on poop, they pick it up on their feet and they take it to to food and they spread it there, and you get it. It's particularly for bacterial causes or other causes that require only a couple organisms to cause illness. So for like Shigella, if you get 10 Shigella organisms, that can cause disease, or norovirus. It's so few particles can cause disease. But a lot of the bacterial requires a much larger inoculum, so it may not be due to flies. But certainly, there's a lot of information that supports that flies are important. So there's been some very nice kind of time series studies where they measure trends of temperature and growth parameters of flies, and then they also, and that really mirrors disease, such as Campylobacter, that follows that trend of fly growth and fly expansion. And then they've actually done some trials and studies where they've controlled fly populations, and such as in the Israeli Defense Force, they control fly populations and they see the incidence of disease goes down. So it's certainly a factor. Some people, depending on the situation, it may be associated with 10% or so, maybe higher if you eliminate the flies. We certainly do that in the military. Whenever you deploy, there's a lot of fly control that goes on where you go. But flies aren't the only thing. And I think what probably best describes the risk of how you get this stuff is what somebody coined as the fecal veneer of the developing world. So there's just a thin layer of poop that covers everything, and it's hard to avoid it. Yes, it's in the food. Yes, it's in the water. Yes, it's on surfaces, and you need to avoid all those things. But there's just a thin layer of contamination that you end up picking up on your hands and putting it in your mouth, and that's what gets you sick.
Nothing will change your view on the world quite like thinking very hard of a fecal veneer.
Yeah, it is a thought.
So, Mark, one of the things I found particularly interesting about your work is that you and others have found that many people with diarrhea actually don't want to treat their diarrhea. Why not? Well,
this is a growing area of discussion, and as I was mentioning, so diarrhea can come in mild forms and severe forms, and it doesn't kill you. You may think that it's going to kill you at the time, but you get through it, and on average it'll last 3 to 5 days, and you'll get through it, and you'll resolve, and we can talk about whether you really resolve. There's also growing concern of chronic problems that occur after acute diarrhea, but in the end, you get over it. And that's coupled with the fact that we're learning more about the potential problems associated with antibiotics. You and your listeners may be very well aware of antibiotic resistance, of the potential effect of antibiotics on your microbiome. So what are we doing to the healthy bacteria in our gut when we take antibiotics? And so coupling these concerns of it'll get better, you just let it, tough it out for a few days, it's going to get better. And if you take antibiotics, you may develop a resistant bug in your system, and you're carrying that around with you, and that may or may not cause harm. That's caused this sort of clinical equipoise of what should we do? Is antibiotics good or antibiotics bad? I can tell you where I fall on the argument, and that is that many of these studies that have been done to look at the potential adverse effects of taking antibiotics are looking at antibiotics that are taken for multiple days and multiple doses. But in fact, what the research I've been doing and our team have been doing is we're getting antibiotic treatment down to a single dose of antibiotic. And so, it's really, you've probably heard of the saying, it's the dose that makes the poison. And we think that just a single dose of antibiotic is much less likely to cause any of these adverse effects. Yet it also is a very effective treatment to change that 3 to 5 day illness down to an illness that lasts 12 hours. So and that's in a nutshell, that's the current controversy.
But there are also people that I was reading about in Mary Roach's book who don't even believe in taking Imodium or something to kind of like stop it up.
Right. And that's, yeah. So I would turn it back. So yeah, you've got this bug that's making all these toxins, and it's, causing you an illness. And do you want to take something that stops up your gut and keeps it in there?
Well, I don't know. Do I?
Well, that's the thought process behind it, is that, oh, I've got this bad bug in my gut. I need to get rid of it. I don't want to keep it in. Imodium, the way Imodium works, it has a anti-secretory, meaning that it causes it decreases the secretions and the water going leaking into your gut, but it also decreases motility, or it decreases the movement of your gut, which is actually causing the diarrhea. Diarrhea is caused by not only more fluid leaking into your gut than it's being absorbed, but also your gut really being hyperactive and trying to move stuff. And so, a natural, a response to an infection then, for someone thinking about it as well, my body's doing its natural thing to try to get it. It's trying to get rid of it with diarrhea. And why should I try to stop that diarrhea? And that's, that's one way of thinking about it. But in all the studies that we've done, it's not really your body that is, responding that way to produce diarrhea. It's partly the bug. The bug's trying to spread itself out in the environment so that it gets perpetuated in the environment. So it's inducing diarrhea so that the bug can survive, and so I think it's a challenge of changing the mindset. But antibiotics in combination with Imodium is really the best treatment for watery diarrhea. And again, if it turns something that could be 3 to 5 days into something that lasts 12 hours or less. And so it's really a very effective combination therapy. And it's been studied that in our studies, and other studies have looked at it, it doesn't come with any significant increased risk. But again, when you're a patient and you're maybe thinking about how your body's working and responding to things, it may seem counterintuitive to try to stop things up, but in fact, that's what works best in treating most watery diarrhea.
But that's, of course, after you've already got diarrhea. You've
Right.
actually been involved in trying to develop vaccines against diarrhea for use in the military and presumably outside of the military as well. But since most diarrhea is caused by bacteria and not viruses, how would a vaccine like that work?
Yeah. And I'll just step back one thing, that why we're developing, since there are such good treatments, one could say, well, you've got good treatments. Why do you want vaccines? Well, I had alluded to it, and I'll speak just a little bit more on why we need vaccines to prevent it in the first place. One is that sometimes it's hard to access care. Sometimes you don't have antibiotics around, or you're in a situation where you can't get treatment. And so we want to prevent it in the first place. But we're also finding is that these infections that are caused, these bacteria and viruses and parasites even that cause these travelers' diarrhea, it doesn't just end when the 5 days later when it's resolved. There's a significant proportion of people that will go on to develop chronic bowel problems like irritable bowel syndrome or constipation or dyspepsia. And so we really think that not only to prevent the acute effects of traveler's diarrhea, but we also want to prevent the long-term health consequences. And so the best way of doing that is preventing the infection in the first place. So moving on to really the question of how do we develop these vaccines? I'm a vaccinologist, or someone that develops vaccines, and I'm probably the first one. Well, I'm not the first one to say, but I'm in agreement that all the easy vaccines have been developed, and so these are hard vaccines. And why are they hard? Well, a lot of these bacteria and these viruses that cause diarrhea, they just stay in the lumen of your intestines. So they don't really invade deeply into the tissues. So most vaccines that are out there, like flu or pneumonia or meningitis, These are systemic infections. So these are infections where the bacteria or the virus invades your body, and it's in your bloodstreams and it's in your tissues. And so it's pretty easy, not pretty easy, but it's easier to develop a vaccine where you give someone a shot and it induces a strong systemic immune response, and so it's effective towards these types of infections. But diarrhea is not an invasive, or not often an invasive infection. Again, it's in the lumen. And so the question, the challenge is, how do you best, initiate an immune response that's just in the lumen? And the best way to do that is actually giving the vaccine orally, or so that it's either causing an infection or your intestines are being exposed to it, and you develop an immune response. And that works pretty well. But the other thing that's challenging is that your body, there's a lot of things that you eat and take in ingestions, and you don't want to develop immune responses to every single thing that you ingest, because then you would be allergic to every single food or everything you put in your mouth. So your body tends towards the position of wanting to allow tolerance to things that you ingest. And so the developing a vaccine to increase the immune response of your gut is a challenge, because your body tends to want to be tolerant of those things that you take through the mouth. So what we've been focusing on are looking at other ways of inducing or creating a good response in the gut. And interestingly, giving things intranasally, so a nose spray, or giving the vaccine on the skin will have an effect of increasing the response in the gut. And so those are some of the things that we're doing to try to make our vaccines target the gut immunology. And then the other things we're trying to use are special adjuvants. And adjuvants are chemicals or proteins that ramp up any immune response. So you give the adjuvants in addition to the parts of the bug that you want to induce a good immune response, and it just makes a stronger and more robust immune response. But with that being said, it's a challenge. I mean, we've been working on Shigella vaccines since World War II, or even before. And so these vaccines that to address traveler's diarrhea are very difficult.
Well, I'm sorry, we are completely out of time. But Mark, thank you so much for taking the time to give us the rundown on the runs. You see what I did there?
Yeah, that was good. That was very good. I hadn't heard that one before.
We've linked to Captain Riddle's research at scienceforthepeople.ca. When we get back, we'll be chatting with Dr. George Peck, who I also found from Mary Roach's new book. George will be taking us on a journey involving another aspect of the fly, its larvae, and how maggots can help wounds heal, if we can only get over the ick factor.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
This is Science for the People. I'm Bethany Brookshire, a writer with Science News and Society for Science in the Public. I'm here with Dr. George Peck, a medical entomologist who is managing a mosquito control district in Oregon. He's an expert in how maggots, yes, fly maggots, can be used to help human wounds heal. I came across him while reading Mary Roach's amazing new book, Grunt, The Curious Science of Humans at War, and I knew I had to take the opportunity to learn more about his work. George, thank you so much for making the time for us.
It's my pleasure.
Now, the procedure that you have been studying for many years is called maggot debridement therapy, or MDT. What is debridement?
Well, debridement is a generic term for the cleansing of wounds, the cleaning of wounds using instruments. At the human scale, that would be scalpels, other instruments that might remove dead and decaying tissue from any type of wound, large or small. In the insect world, with the maggot, the debridement actually occurs at the level of the larval fly. They have teeth that are razor sharp, and they gently, carefully, and joyously imbibe all of the necrotic tissues within wounds that they have infested, and literally clean that tissue right down to the healthy tissue, leaving a perfectly pink bed. And it's really an amazing process.
And debridement, it sounds like you're tearing away or eating away, as in the case of the maggots, tissue. Mm-hmm. Why is debridement important?
From a medical standpoint, it is important because dead tissue would most likely promote the growth of harmful bacteria within a wound. And so to promote healing, of course, the physician would want to remove the dead tissue and allow oxygen to get directly to the living tissue, and to allow that tissue to be free of any bacteria that would be harming the host. In that case, it would be the human.
And you mentioned that maggots joyfully debride these wounds, and I have to say, when I first heard about this, it sounded a bit medieval. Mm-hmm. When did this idea first come about?
Well, the ancients knew that maggots were something that would infest wounds. There's mention of it in the Bible, in the book of Job, where they talk about the maggots eating the wound. And I would suppose that for the Western medical community, that it was during the Civil War when it first became obvious how incredibly useful fly maggots were. Soldiers lay in the field for days sometimes after a battle without any help. And when the physicians would come upon these soldiers, even after days in the field in the middle of the sun, very hot conditions, they would tear off the uniform and find thousands of maggots in some cases infesting their wounds. And when the maggots were brushed aside, what would be revealed were beautiful, pink, healthy, healing tissues. And at that point in time, there was an interest in utilizing maggots for medical purposes. Beyond the Civil War, if we go forward in time roughly to the 1920s, 1930s, William Bayer, after World War I, saw the need for the use of medical maggots on the eastern seaboard, most likely in Baltimore. And there's a fascinating history of Bayer being one of the first people to treat humans with medical maggots and have fantastic results in the clinic.
And is this Bayer as in Bayer aspirin?
No, B-A-U-R, Bayer. This was one of the most famous physicians in the early 20th century. He's famous for many breakthroughs in many areas, and one of them was the employment of fly maggots to aid in the healing process. And
he was working around World War I, but this treatment actually has approval from the American Food and Drug Administration. When did that happen? When did scientists and physicians start taking maggots seriously as a treatment?
Well, there was one individual on the west coast of the United States in the 70s, Ron Sherman. And Ron had trained both as a physician and as an entomologist. And he was working at the VA Center, the Veterans Administration in Long Beach, California. And he noticed that many of the wounds that were being treated were not responding to antibiotics in the most rapid way or the best way possible. And being an entomologist and knowing about the habits of fly maggots and being familiar with the literature on them, as small as it was, he took it upon himself to begin a fly culture right there at the VA Center in Long Beach and began to treat veterans with their permission. And what he found was in cases, say, of a diabetic foot ulcer or wounds that were not responding to normal treatments, he was able to turn around infections and in some cases perhaps even save an amputation.
And when was this approved by the U.S. FDA?
This was approval was I'm going to say around in the mid-90s. And Ron has a facility in Irvine, California that continues to be scrutinized by the FDA. Each year they pass muster. So it's an ongoing process to hold this license for a medical device. And there is a very clean chain of events that occurs at Monarch Labs from the beginning until a shipment of these medical maggots.
So, first of all, I love that maggots are a medical device.
Mm-hmm.
I wonder how the maggots feel about this. But maggots are fly larvae, and flies are usually in contact with a lot of not very clean things. How do scientists go about developing clean fly larvae that are clean enough for medical use?
Mm-hmm. Well, what has been successful for Ron at Monarch Labs and what I did in my laboratory is to allow the adult fly to lay its eggs on a piece of cow liver. The eggs are beautiful white, about 2 millimeters long, and the moment they're deposited on the liver, of course, there's a small amount of bacteria that gets on them. What one can do then is to take these eggs and gently wash them with a weak chlorine bleach solution, and then treat them aseptically and begin a chain of events by monitoring and helping them to hatch and allowing the first, we'd call them the earliest hatchlings, or instar is the technical term in entomology. We'd allow the first instar to have a soy-based broth that is sterile. And that soy-based broth would keep them alive for roughly 24 to 48 hours, just enough time for them to be shipped anywhere in the United States, applied to a wound full of necrotic tissue, which is, of course, their favorite food. And there we have something that starts out a little dirty, remains sterile until it's applied to the wound, and then the healing process begins.
You mentioned necrotic tissue. What exactly does that mean? In what situations are these maggots used for?
One of the best understood and widely studied is in the case of diabetic ulcers. Most of the time it's on the foot, and the patient is not responding to the milieu of chemicals being offered to them, antibiotics and other materials, perhaps antifungals. And as things worsen, in some cases amputation is discussed. If the physician is willing to embrace the maggot debridement technology, through a prescription, they can have these maggots shipped overnight and applied to the wound. And so one would take these very small 2 millimeter long first instar fly maggots and place them on the wound and then cover the wound with a bandage with very strong adhesive to prevent them from escaping. So keeping them right on the wound, allowing airflow into the wound through a screen in the bandage. And the moment those fly maggots taste the dead tissue in that wound, they will begin to ingest it. And this particular species of fly, and only this fly, the technical Latin binomial is Lucilia sericata. We know it as the green bottle fly that we see at our picnics throughout the United States. This particular fly only will eat the dead tissue. And so that's important when one is thinking about this process, because there are many flies that will not stop with the dead necrotic tissue, but will invade living tissue. And this is a bigger issue that is part of the greater world of medical and veterinary entomology.
So I'm particularly amused that maggots are available by prescription.
Indeed.
I suppose it's good they're not over the counter. How does a doctor get maggots shipped in? Does he just call up and say, hey, I need some maggots?
Exactly. Ron's wife, Julie, is on the phone 5 days a week taking calls from all over the United States. The moment the call comes in, the wheels turn. The maggots are taken out of their container where they're being held. Usually they've hatched that morning, and they're placed into plastic vials, which are offered a small amount of the soy broth, sealed tightly. Instructions are placed with them. Perhaps bandages are ordered at the same time, maybe a cold pack to keep them cold as they travel across the country. And they're right next to the John Wayne Airport in Irvine, California, so they can literally put it right onto the jet and have it out there the next day to any clinic. A typical day for Monarch Labs of these fly shipments, I'm thinking they were telling me about 10 shipments a day. Ron actually does practice clinical medicine at clinics away from the laboratory, because it is a small market. So they're kind of on a shoestring, but it is a fascinating technology, and he is the leader in the United States on this technology.
And you mentioned that when the fly larvae get to the patient, they are applied to the wound, and there's a special dressing. How long does treatment with these take?
Well, flies grow rapidly, and the human body temperature promotes this rapid growth. So the nursing staff would be advising the patient to come back the next day and have that bandage removed. And if the chain of logistics is planned correctly, there'll be a second overnight shipment and a second application. And in most cases, the wounds are responding rapidly. Within a week, treatments would cease, and there'd be what we call a pink healthy granulation tissue bed that had formed in the wound, and typical regular prophylactic treatments would continue, and the maggots would not be indicated at that point. It depends on the patient, and it depends on the wound. In the Army, we had to do work where we were working towards simulating IED blasts, the explosive improvised devices that were wounding the soldiers. And so these types of wounds were even more rugged than a typical diabetic ulcer. So we were testing other species of flies that were a little more aggressive in their cleaning action. It's a wide open ball field with these types of therapies. It's very, very interesting.
And you mentioned that the Monarch Laboratory might have 10 or so shipments per day. How widespread is maggot debridement therapy right now?
I would say that it is of worldwide use. When we look at the literature, I would say that the majority of studies have come from Europe, Britain especially, Germany. Less so, there was an Egyptian study. I've seen a few from the Asian continent. And of course, the North American, there's a lot of North American studies as well. And there's a collaborative group of people that work together to promote these types of therapies. And they have a professional scientific society, and there's annual meetings. It can run anywhere from a couple of talks on maggots. There may be a few leech talks. There may even be brought in, say, companion pet talks where psychological benefits are discussed by interacting with animals. So there's really a community of people that want these therapies to be supported and studied and promoted.
And you mentioned, and honestly, I rather agree with you, there's a bit of an ick factor here.
Yeah.
And I'm not an easily grossed out person, but it takes a little getting used to.
Yeah.
How do you think people might go about getting rid of the ick factor?
One way is to change the form of the therapy. For example, one can order from Monarch Labs a maggot sachet, where the maggots are in a soy broth within a sachet, and their excretion and their secretions are allowed to ooze out of the sachet when the sachet is applied to the wound. And so what will happen is there'll be two responses. There'll be a proteolytic response. So the maggots secrete proteolytic enzymes that will break up the dead tissue and make kind of a syrup out of it. And so that's rather than a mechanical removal, there's that effect. And then there's also antibiotics that the maggots excrete. And these have been studied in a very initial way, and there's been papers that have looked at specific proteins being emitted by the maggots that do have a harmful effect on any pathogenic bacteria within the wound. That can decrease the ick factor, put the sachet on, take it off after 24 hours, put a new one on. You never get to see the crawling worms, and you're good.
So it's like maggots in a tea bag.
Yes.
I'm sorry, that's really funny.
Yes. And people really want to move forward with more precise modalities. So people are studying the actual chemical structure of the secretions that are put forth from the maggots and trying to perhaps use those as topical antibiotics. And there's even groups that are attempting to genetically modify the maggots. I was involved in a study with the University of Maryland where we were taking the fly eggs and literally injecting DNA constructs into them with the idea that we would modify the genome, and once we became adept at modification of the genome, introduce novel genes that perhaps could jump the game up so that we'd be making super maggots.
If there's anything better than a maggot, it is a super maggot.
Indeed.
So you mentioned in some of your publications that maggot debridement therapy is actually enjoying kind of a renaissance, partially due to antibiotic resistance. Why is maggot debridement therapy a good choice here?
I would say that we will continue to see resistance, and we will continue to see that bacteria will be one jump ahead of us in terms of modalities where it's one chemical after another, after another, after another. Whereas the ultimate debridement tool, the expert microsurgeon, if you will, is living right in front of us in decomposing organic matter in our backyard, the green bottlefly, Lucilia sericata. And so once we are able to get over the idea that this fly may cause us harm, what we can now embrace is this idea that the fly may save us from having a limb amputated by allowing it to become part of the wound milieu for a moment, for a day, for two, and then let it do its work. And then we've really turned around kind of a losing battle where more and more antibiotics are needed, but fewer and fewer companies are taking on the burden of trying to produce them. So I have great hope for these types of more organic therapies, and I think we should follow the lead of the Europeans, who tend to be more pragmatic about health modalities, and just realize that this is the best way to do things, even though perhaps in our youth we've been told that all insects are gross and we should avoid them.
And you mentioned they do produce an antibiotic of their own.
Yeah, they do. And there's been groups in Czechoslovakia was one of them, and there's been others in the UK that have teased apart the specific components of the maggot secretions and tested them singly for their antibiotic effects against, say, Staph aureus or other pathogens. And they are seeing effects. They're complex proteins. They may not be easily marketable because of their stability. But these are the steps forward that need to happen given our present state of antibiotic resistance and the way that we are in terms of the use of antibiotics.
You've also done some very interesting work involving airlifting maggots, the airworthiness of maggots. Why would you want to airlift a maggot?
Right. Well, again, the military has soldiers coming out of theaters with sometimes terrible recalcitrant wounds that will not respond to any antibiotic available. And what we were hoping to demonstrate was that the maggots would not be affected by the rigors of the medical airlift. And so this occurs in two ways usually. It's the helicopter airlift in the short term near the theater, so maybe from a field hospital to a major hospital, and then from that, say, Kandahar Major Hospital in Afghanistan all the way to the main military hospital in Germany. So that would be a C-130 transport plane. And in these planes, there can be highs and low temperatures. There can be pressure changes. And it's not that we were worried that the maggot would be harmed by this. It's the idea that we had to go through the military's gauntlet of tests to have it be an officially usable medical device on the personnel. And so we literally did that. We let the maggots fly in helicopters. We took pressure measurements, temperature measurements. We measured growth of the maggots. That was the metric. We had a control on the ground, and we saw very little hindrance of growth. Therefore, this particular living medical device was performing beautifully in these medical airlift situations.
I just love the idea of putting maggots in helicopters for science.
Mm-hmm.
In my head, they're wearing little helicopter headphones and have little seatbelts. I'm sure it's not really that cute.
We should make it that cute. I think we really that there's a need to embrace these types of treatments, and I do see a need to lighten it up. Yeah.
So I was wondering, you are working in mosquito control now, and previously you've done all this work with maggots. Mm-hmm. What draws you to medical entomology?
Well, I've loved nature all my life. I've loved the complexity of the living world. I've studied plants. When I first started to study entomology, I realized that instead of conserving insects, what I really needed to be able to get good at was how to destroy them, especially now with mosquito control. But there's an incredible awesomeness to the natural world. And of all of the organisms on the planet, there's more insect species than any other. And it just so happens that if you want to pay the bills, you have to be pragmatic and say, well, I'm finished netting butterflies for the day. I better get back to the lab and show everyone how good these maggots work. So there's kind of a two-sided scientist where there's a need to have your work be seen as useful in the world. But there's also this incredible spirit and this incredible awe that you feel and that you are continuing to move with as the science progresses. And you call it a career. I guess it is, but to me, it's just a lot of fun.
Well, George, thank you so much for telling us about these fascinating creatures and their important role in medicine.
It's my pleasure. Thank you.
We have linked to George Peck's research at scienceforthepeople.ca. There, you'll also find links to Twitter, Facebook, and iTunes, where you can listen to past episodes, subscribe to the show, or leave a review. You'll also find links to our Patreon page, where you can support our fantastic producers and editors with a monthly donation. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Whitten. Coordination and additional behind-the-scenes support comes from the enthusiastic Skepcheck Network team. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. Science for the People is listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount. In return, we regularly post special patron-only extra content and after-show casual conversations with guests. This show is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by Rochelle Saunders and me, Desiree Schell.